This video is for lesson 2 for geometry, and the packet is from the Algebra 1 Mod 1 packet. Lesson 1 was on the structure of a graph, and this one's now on graphing a scenario. I'm also going to incorporate some videos, and since you have the packet, you could type in the hot links in order to be able to see the videos, but we're probably going to play some choppy videos from the sides as you capture my screen. But we'll work through them together. We're going to start with the entry task. Using the graph below, label the origin, the x-axis, and the y-axis. 3 very specific structures of a graph. Then write the ordered pair that describes each shape. From time to time, you'll see me do this as well. I will look up a couple of them, and you'll look up the last. Or I'll do one of them, and then I'll say pause right here. Skip ahead a minute, see if your answer matches mine. Really, again, I strongly recommend that you do that, whether you're watching as a class or by yourself with any video, not just my own. When you're seeking to understand something, you need to really pause it and go try it, and then give a chance to check if you were successful or not. Using the graph below, label the origin. So that's the first thing. That's 0, 0. It's smack dab in the middle. And maybe it deserves some sort of arrow with origin, okay, pointing to it. To label the x-axis, we're just going to make sure that that x stands out along the x-axis and that that y stands out along the y-axis. And I'll write the ordered pair for the triangle. The triangle is located to the right 3 spaces. So 3 is the first number. And then it's located up 1, 2, 3, 4 spaces. So left and right, and then up and down. Same thing for square. Square is located right here from the origin, left 3 spaces, and so -3, and then up 2 spaces. So -3, 2 is the location of the square. Okay, go ahead and pause, skip ahead a minute, but before you do the pentagon and the circle. I'm going to do them right now, I'm not going to talk. Okay, bring it back. So I found the location of the pentagon and the circle, and just check that you did the same thing as well. Let's move on to some notes. We're going to talk about what it means to say that something is an independent variable. If you're in science in any way, an independent might be considered the manipulated variable, the thing that you are allowed to change or affect change. So I might even throw that right here. It's the manipulated variable, and that you are the one that's taking and doing something with it. Formally, or maybe more like, you know, hey, less LeBrant and more Google, is the chance of searching it up and finding that the independent variable is a variable often denoted by x whose variation does not depend on that of another. I'm going to write it all out. You can skip ahead or pause until you get it all written out too. I really just Googled it. A variable often x whose variation does not depend on that of another. Okay, well, how do you know? How do you know that you have the independent variable, the thing that it can change? For one thing, usually in a scenario that involves some sort of a context, time usually is an independent variable. You don't have control over time. Time allows you to determine the cost or to determine the height. It's a factor of speed. Time is a factor of change. So time is something that you don't control it. It exists and it influences something else. How do you know? For example, time is one of them. But the variable influences something else. Okay, that something else is the dependent variable. So a quick search here. I'm just going to type it up. Dependent variable definition. A variable, oh, wow, it's the same thing. A variable y whose value depends on that of another. A variable often known as y whose value depends on another. So it's the variable that is being influenced. I always try to jump to some sort of scenario that says, hey, look at how this is changing that thing. Okay, what is the opposite of manipulated? I need to remind myself because, you know, science. Manipulated variable. What else do we have? Responding variable. Okay. Responding. If it helps for you to equate the two, the manipulated and responding, then use those. In a more mathematical sense, we won't say manipulated and responding, but maybe in a scientific sense we will. I just want to make sure that those are clear things that you can discuss. Go ahead and turn the page. We're on page 6 now. And so page 6 is starting to discover this idea of what we observe in a scenario. Some things we should look for are the independent and dependent. Does it rise? Does it fall? And what are things that you notice? So here's the video. We want to take a look at it. Let's just describe it, and then we'll write some things down. Elevation V for elevation versus time. And the objective here is to guesstimate or provide a picture for what's happening as some dude walks across a bridge. Riveting. It looks like he starts from level. So starts from level. Takes him about 5 seconds to get to the top of the bridge. He pauses for a couple of seconds and then walks down the bridge again. He gets to the end of the video, down to the bottom by 14. Okay. Nope. Don't want to show you yet. Okay. Pauses for 2 seconds. Next, walks down the bridge. Here. Reach over here. Walks down. I mean, these are my notes. I'm going to leave a video for you to do, and you need to decide if my notes are going to help you with that. Walks down the bridge. DGE. Oh my goodness. And done by 14 seconds. Okay. From the very beginning, when it says answer the following questions, what is the independent variable? The independent variable is time. Always. Well, 95% of the time is the independent variable. Time. And again, that's because previously we said it was the variable that influences another, or the variable whose variation does not depend on that of another. So time marches on, whatever the guy is doing. Time is just like 1 second, 2 seconds, 3 seconds. So it's time because the, for one thing, it usually always is the independent. And the key thing is the fact that we're going to say that elevation depends on time. I guess that answers this question. Elevation. Because it depends on time. Okay, so identifying those two things, the independent variable, the dependent variable, we're going to label the axes on the graph below. We're going to make a quick sketch of the answer, and then we'll come back and just check if our math matches theirs. One other thing is, I guess 5 seconds to the top, but I kind of want to go back to the video for a second. I want to see, where does his head start, like where does it appear? Because that's going to depend on our elevation. I guess you can kind of see, that right here where his head is located, it starts to crest over the rail of the bridge. and then it rises, you know, 3 feet. Not a whole lot. I'm going to base this graph upon his relative head height to the rail of the bridge. Wow. I just made that up right now. When I've taught this lesson in the past, I didn't use that. Relative head height to the rail of the bridge. I'm going to say the man is, you know, roughly 6 feet tall, and that a standard rail is, you know, 3 to 3.5 feet tall, 36 inches to 42 inches. And it took 14 seconds. So I know that 0 and 14 are some boundaries to use for seconds along the bottom. And then I guess when he's standing right here, he's at the top of the bridge at his highest point, and this space right here is probably like at most 3 feet. So in my graph, I'm only going to go from 0 to 3, and then this again is in feet. Okay, so at 5 seconds to get to the top, so put a marker for 5 seconds. He stays there for a couple of seconds, maybe 7, maybe 8. I like 8 as a number. And then he walks back down again. So right here from 5 to 8, he is 3 feet. His head is 3 feet over the railing. I don't know. It's kind of tough to see on the far side behind, but using the railing as a suggestion, I'm going to use that right there, that he's level. So up, he walks up for 5 seconds. At the top, he stops. So right here, he's not moving. And then for the remainder of time, he is descending. I think that's probably what the graph looks like. Let's check out the answer. I'm just going to skip ahead on the YouTube video, as you should do for this. They do elevation off of the ground, assuming, you know, what his elevation is already. And yeah, we kind of have that. I mean, our graph's a little more severe, but there's a rise, there's a pause, and then there's a fall again. And so just depending on how accurate you feel like you can be, this really well captures it. Okay, let's try another one. I'm going to get rid of that. So I got my digital file here, looking at things. Again, our video might be choppy because I'm asking my super old laptop to handle a ton of stuff. Get out of here, you. Okay. So we have another scenario, and I think this one, you know, I'll still take the lead on it, but, you know, maybe you can skip ahead. So I'll work, and we'll just watch the video together, and then I'll work quickly. Here we go. Elevation versus time. I'm seeing a pattern. Okay. Oh, I'm ready. I'm set. Let's go. Nice green jacket. Whoa, there's another dude. Oh my gosh, I'm gonna go green and blue. Okay, so 1 second, he starts descending. 3 seconds, 3.5 seconds, he's at the bottom, and then he's back up to the top at 6 seconds. Around flat until 8, 9, and then he starts walking down again. 10, 11. Oh, and at 12, here comes a new one. He walked back up the stairs again. I didn't see that from before. 14 seconds, it's done. Okay. Oh, no, please don't show it yet. Okay. I've already seen the video, if you can't tell. Okay. So, some things I want to do, answer the problems that we have here. What's the independent variable? Time. It's always the independent variable. You know, I should be fair. Kind of always the independent variable. What is the dependent variable? Elevation. Because the man's elevation depends on the time it takes him to, or what specific time that we're talking about. So elevation is it depends on time. Okay, we still have the 14 seconds. And I think what I'm going to do is I'm going to base it on his feet. All right, so height of his feet. Because if I think about it, I need some sort of baseline. Like he's like descending like 6 steps or so. So that's about 4 feet in depth that he's falling down. It's tough to know like his height versus that other man's height, which one is more tall. And so taller. And so therefore I'm going to say the height of his feet is our independent variable. That's the elevation that we're talking about. It's still based on seconds. And we still have 0 seconds to 14 seconds. So I'm going to spread it out like that. Okay, I'm going to put this one on the background on play. And then allow myself to have green for the man and blue for the other man. Checking that they work. They work. Okay. Here it goes. So 1 second, he starts descending. So I'm going to mark that down here. 1. And that he's at an elevation of 4. So from, 0 to 4, that's my interval. And for 1 second in green, the man in green is walking along. That's right, 3.5. He gets to the bottom of the steps. So 1, 2, 3, probably right there. 3.5. He gets to the bottom. So drawing a super steep line, descends 4 feet in that 2.5 seconds, and then boom, he's right back up the other side. There. Oh, pause please. At 5 seconds. Back up to the top. Okay. Oh, by the way, height of feet in feet. Runs around. Right at 9. Right at 9, he's back ready to descend again. So probably right there is 9. So there's a time where his feet are not changing in elevation because he's on the top right here. He's running along the top of the patio. And so right up until about 9 seconds, he's still there. And then he starts to descend the stairs again. So still trying to only focus on him. 10 at the bottom. Oh, he keeps going down. I didn't even notice that. Okay, so not only does he descend the bottom, he turns and continues to walk further on down. I'm going to back up just 1 more second here. Right at 12. That's when this guy walks into frame. So at 12, not only is he down the steps, but he also continues to descend. So this section right here represents he stepped down the stairs and is going down the top flight of stairs to the bottom flight of stairs. And then that's when 13. So for like a second there, what's his face pops into frame, and then how far does he get in that 1 second? He's not at the bottom yet. He's not at the bottom yet. So I'm going to go like this. Yeah, I like that as a graph. I think, here, let me show you. I think that's a pretty good graph. For a second or so, descends the stairs, climbs the stairs, stays on the same level, descends the stairs, descends the second flight of stairs. Oh, and then this other guy pops in. Hello. And he goes down. Ah, lines need labels. So green jacket man and blue shirt man. There we go. Let's check the answer out. I'm going to skip to the end. Okay. Yeah. I don't really know if I buy what's going on over here, but sure, close enough. Okay. All right, so your job is to, this is in your packet, so go find it. This is the video that starts. Watch it, graph it, label it, describe what's happening, and then move on. Think about what's happening in the next exercise. It's still an elevation versus time graph. What did it mean if the line looked like this? Almost answered it. I think you should answer it. What does it mean when the line looks like this? Because it's flat. What's happening to the person as they're traveling? Why is this line steeper than this line? It's flat again. Super steep. Flat. Not really steep at all. But try to come up with some sort of like, what's going on. It can be just the man climbing the stairs. Man, woman, whoever. Climbing the stairs or doing some sort of activity or action. But describe it. Describe how this thing could have a change in elevation and time. Okay, I'll pause and let you do that. The video is going to keep going though. Okay, and bring it back because I want to finish the video. So to finish the video, make sure that you have gone through the closing. The graph in the previous section, elevation versus time, graph of a person's motion, is made by combining pieces of linear functions. It's a piecewise, that's a good word, piecewise linear function. Each linear function is defined over an interval of time. So list those. I'm really curious about these numbers. I don't know if that's right, but the point is I can show you that in this first graph that we did. There's an interval of time, so from 0 to 5 where something happens. There's an interval of time from 5 to 8 where something happens. And then there's an interval of time from 8 to 14 where something happens. These are not ordered pairs like X and Y. No. This is from 0 to 5, and I mean this distance. Then I mean from 5 to 8, and then I mean from 8 to 14. So that's just a little bit different than the entry task or lesson 1 that we just talked about. But these are considered intervals, as in a range of numbers between a lowest number and a highest number. Highest number and lowest, whatever. Okay. So list them. Do the closing. So list them. Okay, learning targets. I can label the origin. Can you? I can identify the independent and dependent variables. I can recognize that an independent variable is X and the dependent variable is Y, and I can label them both on the appropriate axes. That's crucial. I can choose an appropriate scale. You can see how I chose scale because I had a set amount of time. I had to think about my scenario to know that I only really needed like 3 feet. So 0 to 3, perfect. Chose my scale. And then I can create a graph to model a given scenario. Watch the video. This one right here that says the slide. You watch it. Don't look at the answer until the end. And then rate yourself. Let's say 0 to 5. How can you improve? I like what I said in the last video. What would you need to know in order to teach this to someone else? Let's talk exit ticket. The speed of sound at sea level is approximately 340 meters per second. The graph shows the distance d a sound wave created by a loud noise at sea level has traveled after t seconds. Each of the following sets of numbers represent meters, and assuming the graph is correct, which set of numbers is most appropriate to label the 7 tick marks along the vertical axis? That's the distance. Okay. I guess because we're going 1, 2, 3, 4, 5, 6, 7 seconds along the bottom, and speed of sound at sea level is 340 meters per second, the only option is D, so that we could put 340 and 680 and 1020 and ... all the way up to, let's see, oh, I guess I should write it, 1020, 1360, 1700, 2040, etc. It just keeps on going. Option D. Okay, do the problem set. Hang on to these. You'll see how I want to collect them. I'll explain when we get back to school. When I get back to school on Friday. All right, with that, I'm going to get ready to move on to the next lesson. And whether you watch this all in the one day or you do this over a couple of days, study up, do your work. Okay, bye.